My name is Sudhanshu Shankar. I'm a final year undergraduate of the Mechanical Engineering Department. I've done my bachelor thesis project under the supervision of Professor Dilip Kumar Patiyar on the analysis and simulation of our knee orthotic device used to assist people with knee disabilities in walking and daily tasks. The problem I'm working on is to perform a detailed study of the previously developed powered knee orthotic device and rectify the cause of the discrepancy between the simulation and the experimental results. As you can see here, the knee torque values are not matching with the simulation and the experiment. The simulation here shows a parabolic nature. Previously, it was carried out in Adam software with limited detail, and now I have used MATLAB Simscape, which is a multi-body physics modeling technique. I have also attempted to fully simulate the walking of a human with this device attached to his left leg. Here, we will explain the working of the orthotic device. So this part is attached to the thigh and this lower part is attached to the lower leg, and ABC shows the different configurations of the mechanism where B and C belong to the extremes. In the natural position, the spring is at its natural length and the string is taut. At the first dead center, the spring is at its maximum length, and degree to which we need to approach this extreme position is determined by the terrain we are walking on and the maximum knee stiffness which is required. The second dead center shows the maximum knee bending positions. This is the maximum amount the knee can bend, and it is fixed by the dimensions of the mechanism. At the heel strike, where the heel makes the first contact with the ground, the knee bends a little, which is supported by the spring. In this mode, where the motor is not rotating and the knee is supported only by the spring, is known as the passive mode. Other are the two active modes where the spring is stretched and the knee is bent using the wire to achieve the desired gait cycle. Here, we have shown the schematic of the mechanism and the analytical solution for the same. With the equation, I solve the forward kinematics of the mechanism with the link 2 as the input link. This is where the motor is attached. Then, after solving these equations, the natural length of the spring and the length of the string is known. Also, at the knee bending phase, the length of the string is constant, which is a constraint, and is used to solve the rest of the motion of the knee joint. What happens is that when the theta is greater than 90, it's pulls the wire, and because the length of the wire is constant, the knee is bent. On the other hand, when the theta is less than 90, the spring is stretched to provide more stiffness to the knee. Next, we have the gait generation of the walking motion. First, we need to find the trajectory of the center of mass. For this, I have used a 3D linear inverted pendulum model, which is a very good replication of the movement of center of mass while walking. The inverted pendulum here is constrained to move in a plane normal to the ground at the height same as that of the center of mass. The length of the pendulum can change in order to maintain itself in the desired plane. Now, as you can see in the video, the pendulum changes its pivot point in a patterned manner such that the bob of the pendulum generates a symmetric trajectory of the center of mass, and the pivot point represents the fixed leg position at that step. Now we have the video of the mechanism independently and working with the walking robot. As you can see here in the video, the spring is stretched almost half the cycle and this provides extra stiffness to the knee at which the body is balancing. In the next phase, it pulls the string which is used to bend the knee. The fully working simulation was created with the help of multi-body modeling in Simscape. Simscape is a numerical solver which effectively solves the coupled system of 6 non-linear differential equations for each body of the system. Each equation is for 1 degree of freedom of the individual body. This uses the generated trajectory from the inverted pendulum model to attempt walking on the. Here is the flow of calculation explained. The first part is where we specify the height of the center of mass which it is willing to maintain while walking. This fixes the height of the bob of the inverted pendulum, and then the model is used to generate the trajectory of the center of mass and the foot. The trajectory of the foot is converted with respect to the center of mass, and then inverse kinematics algorithm solves the independent joint angles in order to achieve the motion. This is returned in the form of a time series. In the video, you can see how by using inverse kinematics, we are able to determine the joint angles of the pendulum trajectory, which are shown earlier. These joint angles are then fed into the references of both legs, and Simscape numerical solvers solve the effect of the system containing the robot and the ground. In the results part, I'll, uh, I have the torque and the angle plots generated by the analytical solutions. These have been carried out by considering the device alone. The next two plots show the angle and torque plots, which are obtained by fully working model in the Simscape. As you can see, there is slight difference in the angle plot for the fully working model. This shows that the model is able to capture the passive mode heel strike when the knee bends a little as the impact of the ground. The torque plots have some irregularities for the complete working model. This is mainly because of the using a relatively primitive contact model. The primitive, it has helped me a lot to simulate the model faster as compared to a complex contact model. This contact is in the form of four spheres at the corners of the foot. As you can see in the figure, contact happens only at the surfaces of these four spheres. The work ahead will be focused on incorporating more details to the model to better represent the walking motion. Specifically, the foot contact and the movement of the center of pressure is very important to be considered as shown here. Also, I look forward to carry out the experiments again by myself to have a detailed understanding of the experimenting scenario and incorporate the minor details into my model. Also, this work will be evolved further to a design of a controller for the PKOD mechanism, which can alter the reference in real time depending on the speed and style of walking. These are the references I have used. Thank you.